Okay, guys, so we're going to get started with 12.61. This one is a behemoth monster titan of a problem. And so what I'm going to do is I'm going to have you guys get started on it. So if you guys can, this is basically similar to what we went over at the end of the last class. So if you feel comfortable, I really encourage you guys to try it out on your own. You guys can work with someone next to you, but I'm going to go over it very slowly on the screen so that if you are having trouble that you don't get stuck. But if I'm going too slow for you and you want to forge on ahead, please feel free to do that. Okay, so 12.61, so we're talking about a buffer that's made out of acetic acid and sodium acetate. So what I'm going to do first is I'm going to draw a little picture just so we know what the system looks like. So we got 0.3 moles of acetic acid. And then we got 0.3 moles of, what is this? Sodium acetate. Dang, it's too early. Okay, so this is going to be our buffer. Our buffer is made out of these compounds. And it tells you the volume is 1 liter. Okay. So that's the volume. Volume is 1 liter. It also tells you that the pH of this buffer is going to be 4.74. Okay, so there's a couple things that we can figure out about this system. Now, we made the buffer already. So this system is in equilibrium right now. So what that means is we can find a lot of information about this. Okay, so we're not going to make an ice table, but I'm going to write the chemical equations. Dissociation for acetic acid, because we have the Ka, because it goes into equilibrium, right? It's going to be H plus and acetate, the acetate ion. This is the equilibrium that's going on in there. Okay, remember, sodium acetate is a strong electrolyte, so it gets priority in the dissolution. And so what that means is we're going to start off with 0.3 moles of this guy. And then we know that we have 0.3 moles of acetic acid. And then we can find the concentration of H plus by using the pH formula. pH here is equal to 4.74. That's equal to the negative log of the concentration of H plus. Oh, and just to let you guys know, since the volume is 1, the moles are equal to molarity as well. So we can change the molarity if you want. Okay. And so here, since we know the pH, we can calculate for the concentration of H plus. Concentration of H plus, you should get 1.819 times 10 to the negative 5. And that's the concentration of H plus. So we didn't even start the problem yet. All we're doing is figuring out some information about the system. Okay, basically what the information it gives us is the molarity of the acetic acid, the acetate, and the H plus concentration as well. Okay. So far, so good? All right, now this stuff is important because now we can start, we're going to change the system. So we're going to calculate the pH of the solution when we add into this 5 milliliters of a 4 molarity NaOH solution. Now, NaOH is a strong base. So this guy wants to dissolve completely. And so every single mole of NaOH that was added is going to break down. And so we can calculate the moles of NaOH that is added. Okay, so we got 4 molarity NaOH is equal to the moles over the liters. So we need to convert the milliliters into liters. So move the decimal 3 times to the left and you should get 0.005 liters. Okay, all we do is take this information and plug into the molarity formula. that means that the amount of moles that was added is 0.02 moles of NaOH. Another way that you can look at it is that 0.02 moles of OH minus were added. Okay, so this is the amount that was added into our solution for part A. Okay. So far, so good? Making sense? All right, so when you add the base into your buffer, what's going to happen is we're going to get another chemical reaction going. So inside of our solution, we're going to have the acetic acid. And we know that when you add a base, it's going to react with the acid. So the acetic acid is going to react with the hydroxide that was added in there. It's going to go to equilibrium. And then we can write that it forms H2O, water, and it's going to form acetate. Okay, so this is the chemical formula or reaction that takes place when you add the base, because the base that you add, the NaOH, is going to react obviously with the acid, because bases want to neutralize with acids. It doesn't care about the conjugate base, because bases do not react with bases. Okay, so that's why that's where we get this reaction. So far, so good? All right. I know it's a lot, and we're still on part A. Okay, so we're going to set up our ice table now. So let's set that up. Okay, now the first thing that we can do is we can just kind of ignore the column for water, because we know it's a pure substance. We don't count pure liquids. And so let's think about what we had initially. Okay, initially is the stuff that we had before we added the base. Okay, so we're kind of just transferring information from here. Okay, so if you guys look, what was the concentration of CH3COO minus, or COOH, acetic acid? Yeah, 0.3 moles, sorry. How much hydroxide do we have before we added the base? Yeah, none, 0. We didn't have any of this. Okay, we only had acetic acid and acetate. And we can ignore the water, and then this one right here, we just copy that down. It's going to be 0.3 moles. Okay. All right, so now we got to talk about the change. Now, the only real change, or the first change to the system, was when we added hydroxide, right? So we're going to add some hydroxide. So we did all our math. What that tells us is we added 0.02 moles of hydroxide. Okay, now, this is where our ice table changes a little bit from what we had before. We know that the hydroxide is going to react completely with this guy right here, right? So even though the change is plus 0.02, our equilibrium concentration is actually going to be 0, because it's going to react completely. Does that make sense? Since it reacts completely with the acetic acid, we're going to lose all of the hydroxide that we added, which means here we're going to have a 0.02 mole change, but is this going to be positive or negative 0.02? Yeah, it's going to be negative, because what happens is these two guys right here, they're going to neutralize one another. So again, this is a little different from the ice table that we had before, because we added a strong base. And so even though we added it, it gets consumed in the reaction, so we end up with 0. And that's why we lose our acetic acid. And so here, we're going to end up with 0.28 moles of acetic acid. And this makes sense, right? Because if you remember the conceptual stuff we talked about last time, if you add a base, we're naturally going to think that the acid concentration is going to go down, right? And we naturally know that we're going to increase the concentration of the conjugate base. Oh, it's COO minus, sorry. And this conjugate base is going to go up, right? That's just kind of a conceptual thing we talked about last time. And so our ice table should represent what we talked about last time. We added base. that means the acid concentration is going to go down, which is why we're subtracting. And then obviously hydroxide is positive here. And for this guy right here, this is going to have a positive change. Okay, and the magnitude of that change is going to be the same, plus 0.02. And that's going to give us 0.32 moles of conjugate base at equilibrium. Okay, so like I said, same thing basically, just ice table, but we had to keep in mind that the base gets used up completely. All right, any questions so far, or are y'all chilling? That's good. Okay, now I didn't mention this, which is bad because we should always look at this. What we're looking for in this problem is we're trying to calculate the pH of this solution, okay? So what we're gonna do is we're gonna use that new pH formula that we talked about last time, because here we don't have a equation, right? Or we don't have a value for the concentration of H+. Luckily, we have the new pH equation we learned about last time. We know that pH is going to equal to the pKa plus the log of the base divided by the concentration of the acid. Okay, so this is the new pH formula that we learned last time. And so I'm going to give you guys about a minute. See if you guys can plug in, excuse me, the values that we have. You have everything you need to find the pH now. We just need to plug it into that formula. Okay, so I'll give you guys about a minute to do that. And then we'll get the final answer for part A. Alrighty, guys, so let's plug in the values that we have. If you're still finishing up, please feel free to finish up, but I'm gonna start going over it. So we have the Ka for acetic acid. It's 1.8 times 10 to the negative 5. So if we find the log of that value, you should get 4.744. Oh, hold up, did I copy the equation down correctly? Is it negative or positive? Sorry, guys. Double checking. Oh, we're good. This one, right? Yeah. So we should get negative 4.744. Everyone got that? Okay. And then we're gonna add that with the log of the concentration of base divided by the concentration of the acid. Now, we need to be very careful here because we have to divide by the volume, which is not 1 anymore, okay? So it's gonna be a very small difference, but if you guys notice, we added 5 milliliters, right? So if our starting volume was 1 and we added 5 milliliters, we have a new volume, right? Because we added some liquid that changes the volume. So the new volume is no longer 1. It's going to be 1.005 liters. I know, it's kind of annoying. It's going to make a very small difference, but they will look for that in the calculations on the AP test. Yeah, what's up? Did I plug it in wrong? It's the log of 1.8 times 10 to the negative 5, right? In the equation, is this the negative log? Hold up. Mr. O is old. I did the same thing for like one other problem. It is the negative log. Sorry, guys. Yeah, so positive. I knew that. I was just testing y'all. Thank you for being aware. Okay, so yeah, 4.744. Okay, so now we need to recalculate the molarity for the acid and the base. So what we have to do is we need to take these values right here and we need to divide that by 1.005 liters, okay? Now, it's going to make a very, very small difference. But like I said, on the AP test, your grader will look for that to see if you're going to notice the change in volume because it will change up your calculations. So the concentration for the acid is 0.28 divided by 1.005. And you should get a value of 0.27. I'm gonna round that up to 9. So we're going to do the log of 0.279 on the bottom. And then for your base, 0.32 divided by 1.005, that's going to give you 0.318. And that's what's going to go on the top. Okay, and then so we're going to do the log of 0.318 divided by 0.279. That's going to get us a value right here. The log is going to become 0.05. I'm going to round that to 7. 4.74. So we're going to add those two together, and you should get a value of about 4.797. And so that is going to be the pH of your buffer after you add the sodium hydroxide in it. Yeah, what's up? Yeah, it's because you added 5 milliliters of base, so that's going to change the volume, right? If you pour something into 1 liters, it's not going to be 1 liter anymore. It's going to go up in volume, and so that's why it's 1.005. It's 1 liter plus 5 milliliters. Okay. Any other questions? Huh? What'd you get? 4.08. That's fine. That's close enough. Usually if you're within 5%, that's fine. And it's because of the volume. Okay, so let's make sure you guys write that down somewhere. We're gonna finish part B. Part B is a lot easier. Okay, so make sure you write 4.797 for the pH. Okay, so if you guys notice, the pH did not change very much, right? It changed less than 0.1. And so in a buffer, you're changing, if you add 5 milliliters of a strong base, it'll only take it from 4.74 to 4.79. And again, it's because buffers resist pH change. Now we're going to compare that to see what happens when we add the same amount of base into pure water. Okay, so same thing. We have 5 milliliters of our, what is this? Of our base. It's going to be 5 molarity, so same concentration. And so that means we're going to be adding the same amount of base, right? We're going to be adding 0.02 moles of NaOH. And this time we're going to be adding it to 1 liter of pure water. All right, so all we need to do right here is we need to calculate the molarity of the base or the hydroxide inside of our water. And so all we need to do is divide this value by the new volume. It's going to be 1.005 liters, same thing as before. And then if you divide it, you should get a value of basically the same things, 0.02 molarity. So again, this volume change does not make a big difference, but on the AP test, they will be looking for whether or not you're using the new volume, okay? All right, so if you have this value, what we can do is we can calculate the pOH, right? We can do the negative log of the concentration of OH, and then we can use the formula for pH plus pOH equals 14. And that will allow you to find the pH of water when we add 5 milliliters of base. So take a second to calculate that out, and then you guys will see how much the concentration changes in pure water if you add 5 milliliters of strong base. It's going to be a pretty big change, so please expect a big number. So I'll give you guys 30 more seconds to finish that up. Alrighty, guys. So your pH will be 12.3, around there. So you guys can tell that buffers really work, right? Buffers want to resist the pH change, because even though you're only adding 5 milliliters to pure water, it's going to go from 7 to 12.3 if you add 5 milliliters of strong base. But if you have a buffer, adding 5 milliliters of strong base only changes it about like 0.05 in the pH. Okay, so very small difference. So that's how buffers resist pH change. Any questions? Alrighty, let us move on to, I guess, the last and one of the bigger topics for this class. We've actually done this already, so this should kind of be a refresher. You guys remember acid-base titrations, where you drop the base from a burette into a beaker? We did a lab for this one. And so basically what acid-base titrations do is it allows us to find the equivalence point. Okay, you guys might want to write that down. Equivalence point is basically where the acid and the base have completely neutralized one another inside of your solution. So it allows you to find the concentration of an acid by adding an amount of base into it. And so what we can do is we can calculate the pH of a solution at different points of a titration. Okay, so titrations are basically used to find the concentration of an unknown solution by adding the opposite one into it. Okay, usually base into acid. Okay, so don't worry about writing this down, okay, because we're not going to spend too much time. We already did this, okay? Strong acid to strong base. Basically, since strong acids and strong bases dissociate completely, right? It's very easy for us to find out how many moles of H we added, how many moles of OH we added. Okay, and so when we have a strong acid, strong base titration, it's a very simple calculation. We just need to figure out how much H plus or OH minus is in there. That's going to let us find the pH. Okay, and then as you add some of the base into the acid, it's going to slowly increase. And then equivalence point is when there are equal amounts of acid and base, they completely neutralize each other, and that's 7. And then afterwards, there's only base left. So don't write this down. We already did this back in Unit 4. And you might need a quick refresher, but we're going to go into some tougher calculations instead of this one, okay? So we're going to skip that one. We're going to skip that one. We're going to skip that one. Actually, we'll do one. Okay. So I want you guys to try this out on your own. I'm gonna give you guys 3 minutes. This is basic stoichiometry, should be pretty simple, just molarity and stoichiometry calculations only. I want you guys to calculate how many liters of 3.4 molarity HCl is required to reach the equivalence point with 2.1 liters of 2 molarity KOH. 12 liters of base, that's a lot. Okay, so basically what you're doing is you got a, 3.4 molarity HCl solution. You're going to be adding base to it, 2 molarity KOH. You added 2.1 liters of it, and you need to find out how many HCl, or how much HCl, the volume of HCl in here. Okay. All right, so I'll give you guys 2 minutes. This should be really easy, just to be frank with you. It's just basic stoic and molarity. Just take about 2 minutes to try that out, and then we'll go over it together. Okay, so from here, you should be able to identify the reaction. Super simple, strong acid plus strong base goes almost completely, or if not completely, to water and salt, KCl. And you should be able to use these values right here, 2 molarity and 2.1 liters, to figure out that this means that we added 4.2 moles of KOH. What that means is we need the exact same number. We need 4.2 moles of HCl in order to neutralize the KOH, right? Because it's a 1-to-1 stoichiometric ratio. That's a hard word, okay? And if you need 4.2 moles and you have the molarity, that's a very simple problem. It's just molarity is moles over liters. We're looking for volume anyway. So our volume is going to be moles divided by molarity. And then so you're just going to plug that in. And then that should give you a final answer of about 1.235 liters of your HCl solution. Okay. So titration with a strong acid and strong base is very easy, just because it goes to completion, right? The acid dissociates completely, the base dissociates completely. You make all water, all salt, and then there's no equilibrium. So we don't need to do an ice table, just need to look at the ratios. And this is what we did back in Unit 4. But you guys are much more advanced now. Yeah. Yes, you could have used that formula as well. So there's multiple ways to get to this answer. So if you use the dilution formula, that's shown too. Whatever works. It's a good way. I didn't even think about doing it that way. Just be careful with that, Janelle, because it has to be a 1-to-1 ratio. And so if it's a 2-to-1 ratio, like if you use sulfuric acid or something like that, you would have to adjust for it. Okay, let's move on now. So we talked about strong acid, strong base, and those are very easy because they break apart completely. But weak acids, like people, are a little bit more complicated. Sometimes they break up and then get back together, and then that's how weak bases work. So first, we're going to look at weak acid, strong base titrations. Okay, so if you guys notice, the titration curve is already going to look a little bit different. I want you guys to draw the titration curve right here. Don't make it super detailed, but what I really want you guys to notice is that there's a big difference in the way the pH changes over volume. So if you have a strong acid, strong base, it's a very sharp curve. So it goes flat, and then as it reaches the equivalence point, it goes almost vertical, and then it flattens out again. Okay. The weak acid, strong base is similar, but if you guys notice, the slope right here is a bit steeper, right? So it changes a little bit faster than the strong acid, strong base. Okay, do you guys notice that? The strong acid, strong base, it goes very flat. It's a very flat slope, and then it goes super vertical and then flattens out again. The weak acid, strong base, it has more of a slope, so the rate of change is going to be a little bit faster, and then it goes flat for the equivalence point, and then the ending is pretty much the same as the strong acid, strong base. So just keep that in mind. That's actually kind of a good way for you to keep in mind what the pH change should look like. You got strong acid, strong base. it will change very little until it gets to the equivalence point. Strong acid, strong base, not so much. There's more of a change. All right. Make sense? Can we move on? Please let me know if I'm going too fast. Okay, so I have all these different steps. This is kind of something you can go back to for your notes. This came from your book. I think it's a little bit excessive. I think doing practice problems a lot easier, but these are the steps for finding the pH at various points for weak acid, strong base. We're going to skip all that, and we're going to go straight into the problem. Okay, 12.65. Okay, so here, let's kind of draw out what is going on in this situation. So it's asking us to calculate the pH of the solution formed when 45 milliliters of 0.1 molarity NaOH, so basically we're dropping the base, we're dropping 45 milliliters. I'm going to change that up to 0.045 liters of 0.1 molarity NaOH. Your base is added to your acid, and you're adding it to 0.05 liters of 0.1 molarity acetic acid. And so if you guys notice, we are adding a strong base into a weak acid. And then we got the Ka, and we're trying to find the pH of this solution. All right, so far so good. Okay, what I want you guys to do is I want you to calculate. I want you to calculate the moles of both of these. So I want you to figure out how many moles of base we have in the system, how many moles of acid we have in this system. Okay, that's the first thing that we want to do. So take about 40 seconds, should be pretty quick. I want you to calculate the moles that we have for both in this system while I wait for puberty to kick in. Okay, guys, so the moles should have been really easy to find. For your base, you should have gotten 4.5 times 10 to the negative 3 moles of NaOH. And then for your acid, you should have gotten 5 times 10 to the negative 3 moles of your acetic acid. And I'm just going to write HA, because that's a long formula. All right, so far so good? Okay, now if we take a look at these two, which one has priority in terms of dissociation? Yeah, NaOH, a strong base, will have priority in dissociation. And so what we're going to do is we're going to write the chemical equation. So we know that acetic acid is going to react with the hydroxide because it dissociates completely. And then what's going to happen is it's going to form water, and it's going to form acetate. Okay. And then we're going to set up our ice table. Now, this is a very similar ice table to what we did earlier. So I know that titrations might seem like, ooh, there's like multiple parts, right? Because you need to figure out before we reach the equivalence point, at the equivalence point, after the equivalence point. Honestly, all that stuff does not matter because you can just figure out how many moles you added, and then it's the same calculation after that. So don't get freaked out if you see the word titration. It's literally the same thing that we've been doing. It's just adding a strong base to a weak acid and vice versa. Okay. So we can ignore the pure compound. We can ignore H2O. And then we can start plugging in our value. So since we have the Ka, we're going to be looking at the acid system right here, okay? So initial is going to be referring to the acid system. So initially, how many moles of acetic acid do we have? How many moles? We're going to use moles. Yeah, 5 times 10 to the negative 3. Okay, and we want to specify moles. The reason why we don't want to use molarity with buffers and titration is because the volume changes, right? Because we have liters here, they're going to change over time. Okay, how many moles of hydroxide did you have in your acid system? None, 0. Zip, nada. Okay. And then for your acetate, we have 0 as well because it's accounted for inside the acetic acid. That's chilling. Okay, so if we add sodium hydroxide to it, again, we get priority with the sodium hydroxide, right? So plus 4.5 times 10 to the negative 3 moles. Now this guy right here is going to dissociate completely. So how much hydroxide will we have at equilibrium? 0, yeah. Now one thing I do want to mention is it's 0 because we have more moles of your acid than you have of your base, right? Obviously, if you have more base than your acid, you're going to have to remember that you will have some hydroxide left over, okay? So just keep that in mind. So for example, let's say you added, I don't know, 6 times 10 to the 3, negative 3. If this is your change at equilibrium, since you only have 5 times 10 to the 3 moles, you're going to end up with 1 times 10 to the negative 3 moles of your hydroxide. Okay, so you only put 0 if you have more acid, but if you have more base, you're going to have to find the difference because you'll still have some base left over. Okay, so just keep that in mind. Might be helpful later. Hint, hint. Okay, and that means we're going to lose the same amount here because it's going to react with our base, 4.5 times 10 to the negative 3 moles. And then we're going to end up with 0.5 times 10 to the 3 moles. We just did 5 minus 4.5 and then kept the scientific or kept the exponent. Okay, which means we're going to gain the same amount for our acetate, 4.5 times 10 to the negative 3. And then so we're going to end with 4.5 times 10 to the negative 3 moles. Okay, so there you go. That's our ice table for the system. All right, and then from here, it's very similar to what we have been doing, or actually we can't use the buffer system. Never mind, sorry. Actually, we can use the buffer system. Yeah, we can. Okay, so from here, first thing we want to do is figure out the new volume. So the total volume now is going to be 45 milliliters plus 50 milliliters. So that's going to lead us to get 0.095 liters. That's our new volume. Okay, and you guys should have everything that you need now to calculate for the pH. So I'll give you guys about a minute and a half to calculate the pH for this system, and then we'll be all done. Oh, I'm so dumb. pKa is always negative. I just realized why it was negative. Sorry, guys. Remember earlier how I put negative? It's because I didn't do negative log. And I was like, why is it not negative log? But it's because pKa, P necessitates negative. Wow. Yeah, I'm getting so old and dumb sometimes. Something close is fine. 5.7. I got 5.7 the first time I did it. You subtracted somewhere when you should have added. Check your pKa. You might have done what I did. Your pKa should be your pK is 4.744 plus 0.948. Everyone got that? 5.7, 5.69? Something close. Yeah, nice. All right, guys, so that's titration with a weak acid and strong base. So as you guys can see, a lot of this stuff is basically the same thing. We really haven't been doing anything new, right? It's just ice table, equilibrium, Ka, and then molarity. That's like the four things that make up this unit. You just need to be able to apply the concepts in different situations. All right, I'm going to give you guys a 5-minute break, and then after that, we're going to come back and finish up the lesson. If you guys have any questions, please ask me during the break. Can't talk today. And so you guys can go to the restroom if you need to. We'll come back in 5 minutes. Okay, so for 12.67, this one's very deceptive because it starts off seeming really easy. You get the, the volume and the molarity of the acid. You get the molarity of the strong base. And then saying to calculate the pH at the equivalence point. Now, if you guys remember from the definitions, equivalence point is where the acid and base completely neutralize one another, right? And so here, you can calculate that you have 0.005 moles of acetic acid. And so obviously, in order to neutralize that, you'll need the same amount of base, right? So you need 0.005 moles of sodium hydroxide. And so we can set up a very simple ice table. And we're going to just plug in the values that we have. We have 0.005 moles of acetic acid. In the beginning, we start with no sodium hydroxide. I guess, okay, sorry, not sodium hydroxide. We want to do hydroxide ion. My fault. And then we start with no acetate. Okay, and then we're going to add 0.005 moles of sodium hydroxide. So it's minus 0.005 moles. This is going to react with this guy right here, or sorry, plus. Oh my gosh, I'm out of here. And then this will react completely, and so you'll get minus 0.005 moles. And then the problem that you're going to encounter is that you end up with no acid, no base. And so how do you calculate pH, right? If you don't have any acid or base. And so what we actually need to do is finish up the ice table. And so if you consume 0.005 moles of acid with the base, that means you're going to gain some of this guy right here, 0.005 moles. And so you're going to end up with 0.005 moles of acetate. Okay. And this is where you should get stuck because you don't have anything to plug in to get the pH, right? All of your pH formulas fail. You have pH is the negative log of H plus. That doesn't work. You don't have H plus. You could try using POH to kind of find the other one, but you have OH minus and it's 0, so it's not going to work. You can use the other one. We have pH equals pKa plus the log of base divided by acid. That doesn't work because you can't divide by 0. And so it's kind of like, what do I do? And so here we have to think a little bit outside the box. And so what I want you guys to do right now is turn your attention to this last compound right here. What's this thing called? Acetate. Now acetate, we have some acetate left, right? So once the entire reaction goes, we have acetate. Now, let me ask you guys, what kind of compound is acetate? Yeah, it's a weak base, right? It's a conjugate base. So all of the acid, all of the base have been neutralized. The only thing you have left over in your container now is your weak base, and what other compound is in there? Agua. Yeah, agua. And so if you have a weak base in water, what do they like to do with each other? Yeah, they like to go equilibrium. And so you can write a new equation. I don't know, isn't chemistry so fun? It's so creative. It's like art. Probably not. Okay. And then you're going to create a second ice table, and you're going to plug in your value. So you have no water you can ignore because pure compound. And then you can take your equilibrium value of acetate and plug it in right here as your initial value. Okay. Now, before, actually, you can do it like this too. This works. Oh, not molarity. All right. Do you guys think you could finish it up from here? Maybe. There might be another wall. Hopefully not. But I'll give you guys another 2 minutes. Just try wrestling through it. This is kind of how you figure out and really master these problems.
Because I remember you said something about.
But I'm going to go over the rest of the problem now, okay? So if you fill out the rest of the ice table, you should recognize you have no acetic acid, right? Because it got neutralized in the beginning. You don't have any hydroxide because it got neutralized in the beginning. Basically, all you're doing is you're taking the equilibrium values and bringing them to the new initial state. Because what happened was the acid, the base, they reacted. It's all gone. And all it makes is the acetate ion. Okay, now, in real life, this all happens like in a process. So it's not like instantly gone and then we wait for all the acetate to make it. It's like it goes as a process. But mathematically, this is the way that we can look at it. And so from this equilibrium arises a new system. And so we have our new initial state, which is the same thing as this equilibrium state. Okay, it's going to react with water. And so obviously we're going to lose some of the acetate. We're going to gain acetic acid. We're going to gain the hydroxide. This is just a normal, easy ice table. And then we got 0.005 minus x. We got plus x. And then we got x. Okay. And so now we can start plugging in the values. Now, be very careful because this guy right here, what did we say the type of compound it is? Yeah, it's a weak base. If it's a weak base, can we use the Ka? No, we cannot use the Ka. What do we need to use? I told you guys this problem just takes you, not the Kw. We need to use the Kw to find what though? Kb, yes. We cannot use Ka. So yeah, this problem is a bad ex-girlfriend / boyfriend. It just gives you a little hope and then brings you down, brings you a little hope, brings you down again. So yeah, guessing you guys all did it wrong. So we got Kb. And so what we need to do is we cannot use 1.8 because that is the Ka. You got it, Ethan? You stud. Okay, so what we need to do is we need to use the Kw formula, which is Ka times Kb. We can rearrange it so that Kb is equal to Kw over Ka. And I'm going to give you the Kb value just to make your life a little easier. I've tortured you enough today. It's going to be 5.6 times 10 to the negative 10. So that is the Kb value for your acetate. Okay, so be very careful because people will try to mess with you like this. That's why I don't trust people. Anyway, that's my problems. So Kb is equal to the products. So x squared divided by 0.005 minus x. So we got the product concentration on the top, reactant concentration on the bottom. And then luckily for you, you don't need to use the quadratic here because the Kb value is so low. So we're going to ignore the change. That makes it a lot easier. And so we'll just get an equation where we get a final answer of x is equal to 5.3 times 10 to the negative 6 molarity. And now that we have x, we have a value for OH. And so from that, we can find the POH. So POH is the negative log of 5.3 times 10 to the negative 6. Oh, I'm getting tired teaching this. 5.28, and then we just need to subtract that from 14, and we'll get a pH value of 8.72. And there you go. So the equivalence point in this titration, the pH is going to be 8.72. That is when all of the base and all of the acid has neutralized with one another. Now you might think this doesn't make any sense. If the acid and base neutralize each other, why is it basic, right? Why isn't it 7? But it's because we're gonna have some leftover Kb, which is a base, and that's gonna force the solution into basicity. Okay, so that was a lot. That was actually a very tough problem. If I gave this to all the chem teachers in the district, I think maybe 3 or 4 out of 10 would get it right. So don't feel too bad. This is a hard problem. Yeah, what's up? For X, let me do. Oh, well, I guess now make it 5 out of 10, 1 out of 2, because I got it wrong too. 5.6, 10, negative 10 times 0.005. 2.8 times 10 to so square root 2.8 times 10 to the negative 12. I did 2. 1.6 times 10 to the negative 6. Dang, I'm dumb. 1.67. And then so you can plug that in there. 1.67. So I guess I would get it wrong too, but so negative log the answer. So your POH should be 5.77. And so you should get 8.22 as your pH. Sorry, guys. I'm blaming Pepik. Even though he didn't do this problem in the book, I'll say it was him. Alrighty, guys. Congratulations. That's the last hard part of Unit 12, the longest and most important unit of the year. All right, so I did say we do have a small, yeah, what's up? Yeah, I mean, POH is the negative log of the concentration of hydroxide, right? If we find X using the Kb formula, we can get the concentration of hydroxide. And all we did was plug it in to that equation. Because we gained X from 0 because we needed to lose the weak base. So we gain the same ratio for OH. Kb, we solve for X, and that gives us 1.67 times 10 to the negative 6. Okay, so I did say that we need to do one last section. It's like 3 minutes. It's really quick. And the reason why we only have one more section is because a lot of this you have to read on your own. So, but I know you guys all keep up with your reading. Good, I'm glad. Okay, so we're gonna talk about solubility equilibria. This is very, very simple. We talked about solubility before, right? Whether something dissolves or not. So if you don't remember, please refer back to Unit 4 because that will be important. Basically, solubility tells you, is a compound gonna dissolve in your solvent? So usually water. Is this chemical gonna dissolve in water? That's the easiest way to think about it. Okay, now there is a constant for that. Okay, and that's called the KSP. You guys are probably tired of that letter now. K. KW, KA, KB, KSP, KEQ. What else do we have? I think that's it. But KSP is the solubility product constant. And basically what it tells us is it tells us whether or how likely it is for something to dissolve inside of a solution. Okay, that's pretty much, or yeah, that's pretty much it. Okay, and all we really need to know how to do is how to write the expression. It's the same thing as all the other K expressions. You just need to write the products divided by the reactants. So we have an example right here. We have barium sulfate, and we're gonna see what if this thing dissolves inside of a solution. Barium sulfate is a solid, a pure substance, so we can ignore it inside of the KSP formula. So all we need to do is product concentrations divided by reactant, since we can ignore pure compounds. There you go. That's how you write the KSP expression. That's it. Super easy. So with that being said, let's do the last problem of the unit. I want you guys to try 12.69. want you to write the solubility product constant for CaF2, calcium fluoride. And after that, we are all done though. All right, another 30 seconds and then we'll go over it. Alrighty, guys, let's go over 12.69 and then we're done for today and the unit, okay? So we have our solid, we have calcium fluoride, and this is gonna be our solid because we're trying to dissolve it. And then we are going to put it inside of a solvent, and then it's gonna decompose into calcium ion, which is aqueous, and then it's gonna decompose into fluoride ion, which is aqueous. However, how many fluoride ions do we have? 2, yeah, so we need the coefficient. That's gonna change up our KSP value because what we have to do is we can ignore the solid, but we need to do the concentration of the calcium ion. And then we have to do the concentration of the fluoride ion, but what do we need to add to the fluoride ion? Yeah, exponent of 2. And there you go. So just keep in mind that you will have to include, excuse me, Bill, you have to include the coefficient as the exponent. I know we haven't done that in a while since we've been doing one-to-one stoichiometry, stoichiometric reactions, but please keep in mind for the equilibrium constants, we have to do the coefficients as exponents. All right, and honestly, guys, congratulations. That was a crazy unit. I'm actually surprised we got through it in 2.5 weeks. You guys really pushed, so props to you on that. But that's pretty much it. Next time that we meet on Friday, again, we're not taking the test. We are going to practice. We're going to do some practice problems for the test, and then we will take the exam on Tuesday. And then after that, we have 2 units left, but they're only about 1 to 2 class sessions each. So that'll go by really quick, all right? And after that, it's review until the exam. And so, yeah.